Section 2.4, we're going to continue working on limits. We're going to introduce what are called one-sided limits. And we see an example of that with problem number 14. Limit as x approaches 10, and there's this little sign here, plus 10 from the positive side or the right side. And let me try and help you understand what that's all about. So there's two different directions that you can approach the number 10 from on the number line. You can approach it from the right or from the left. Now, we call this the positive and negative sides, basically because if you were at 0, the positive side is going to be to the right and the negative side is going to be to the left. So approaching from the positive side means you're approaching from the right. Approaching from the negative side means you're approaching from the left. And sometimes that makes a difference. For instance, with this problem, let's take a look at the graph. Here's your function, the absolute value of x minus 10 divided by x minus 10. Now we want to find the limit of that. What's the limit as you approach from the right? The limit's not 10. What's the limit? 1, right? You're looking for the y coordinate there. So the limit as x approaches 10 from the positive side is 1. Let's change things up a little bit. What if I ask you the limit as x approaches 10 from the negative side of the absolute value of x minus 10 over x minus 10? Yeah, let's take a look back at the graph. But as you approach from the left, now you're at -1. So in this case, it makes a difference as to which limit you're using. So that's -1. Let me ask you kind of a follow-up question. The limit as x approaches 10 of the absolute value of x minus 10 over x minus 10. Does not exist. Good. Remember, in order for a limit to exist, the limit from the right and the limit from the left have to be equal. I've been going over that since day one. That is, the limit from both sides have to equal in order for the limit to exist. If you look back at some of my old exams online, a lot of times I'll walk you through things like this. I'll ask you to calculate this, this, and then this. And hopefully that's kind of like leading you through to this conclusion that, oh, wait a minute, these two don't equal, therefore that does not exist. Absolute values. Let's back up a step. Take a look at problem number, let's see, problem number 10. The limit as x approaches 4 from the right of 4 minus x over x squared minus 16. Now, generally speaking, when you're faced with something like this, you look at that and go, oh, gee, if I tried plugging in the limit, I end up with 0 over 0. You know, sometimes you might think that because 4 creates a 0 in the denominator, you're going to have a vertical asymptote. Well, you might not. In this case, though, let's play around with the function sum. And this is another example of factoring out that negative. Because in the denominator, when I factor out the denominator, I get x minus 4 times x plus 4. Doesn't quite match what I have in the numerator. So how can I flip this around? What else could I write up here? Yeah, factor out the negative. Negative of x minus 4. So that's that factorization again that we saw in the last section. Now this will cancel, and we're left with the limit as x approaches 4 from the right of negative 1 over x plus 4. What's that limit going to give me? Yeah, thank you. Negative 1 over 8. Let's look at the graph here, because we actually got a limit out of this and understand something about the graph and the nature of what we're going to see when we graph that. So let's see, do I have that one in here? No, I don't. So let's put it in here. Y equals 4 minus x divided by x squared minus 16. Now, generally speaking, you would probably expect to see some kind of an asymptote at x equals 4. But let's instead see what we get. At x equals 4, the function's nice and well defined. Now that's in contrast to what you see at x equals negative 4. Let me look back at our function real quick. When this factored, you have x minus 4 and x plus 4. At x plus 4, what's the value of x that makes that equal to 0? Negative 4. Let's look at the graph at negative 4. You've got this vertical asymptote. But we don't have that over here at x equals 4. In fact, the function looks pretty well behaved. It's coming closer and closer to negative 0.125, except when we get to positive 4 itself, it's briefly undefined. And there we go. It's undefined there. That's okay. The limit still exists. It's still negative 1/8. But there's a hole in that graph. And let's talk about such holes, those discontinuities. There's a couple varieties of discontinuities, and one of them is the kind that we see when we see that hole. So let's flip over in our books to page 91. What we have there is called a removable discontinuity. So what that means is that I can redefine the function at this point and it'll be a nice, smooth, continuous function. So I could fill in that hole if I wanted to by just redefining the function at that one point. Let's move down to figure C. This is another removable discontinuity. Because again, if I take and redefine the function, if I pick that point up, I can fill in that hole and it'll be a nice, smooth, continuous function. By that I mean I can draw it without lifting my pen from the paper. That's what I mean by a continuous function. Now, that's not a formal definition, but it's a good working definition. Let's take a look at the last example on page 91 here. Can I redefine the function at this point so that this is a continuous function? No. There's always going to be this jump discontinuity here. So this is a non-removable discontinuity. I can't get rid of it. I can't redefine the function to make this friendlier, make it continuous. So you've got two different types of discontinuities: removable discontinuities and non-removable discontinuities. Let's take a look at a couple problems in the book now. Problem number 20. The limit as x approaches pi over 2 of the secant of x. Some of you might be more comfortable thinking about this as the reciprocal of the cosine. So that's 1 over the cosine of x. You don't have to, but maybe you're a little bit more in your comfort zone there. Well, let's take a look at this graphically and see what we can see. So let's get rid of this one and turn on these two. So in green is the graph of the secant function, and in purple you've got the line x equals pi over 2. Let's do this. Let's kind of mix up the work a little bit. Let's do the limit as x approaches pi over 2 from the left of 1 over cosine of x. Limit as x approaches pi over 2 from the right of 1 over cosine of x. And then we'll fill in that last one. So this is a nice progression. You've got the left-hand limit, the right-hand limit, and then the overall limit. So we'll do all three. So what's the limit as x approaches pi over 2 from the left? As you get close, as the value of x gets close to this purple line from the left, that is from the negative side of things, where's the value of the secant going? Infinity. So the limit from the left is positive infinity. What's the limit from the right? Negative infinity. So as you approach from the right, this function is going towards negative infinity. So the limit from the left is positive infinity, the limit from the right is negative infinity. What's the overall limit? Does not exist. These two would have to equal in order for that to exist. Now often the book is just going to ask you what the limit is. But keep in mind, in working with the limit, you always have to consider these two things. The limit from the left and the limit from the right. Let's try problem number 26. In fact, I want you to try problem number 26. I'll give you a heads up. You're not going to be able to do it graphically, or you're not going to be able to do it analytically. There's no multiplying by the conjugate or rationalizing a numerator or denominator. You're just going to have to work it out some other way. You want to look at the limit as x approaches 6 from the negative side of the ln of 6 minus x. Now, if I'm telling you you can't do it algebraically, you can't do it the way we were doing some of the limits in section 2.3, what other options do you have? Graphically or numerically. All right, so plug it into your calculator and start looking at it graphically or numerically. Now keep in mind you're approaching negative 6, or you're approaching positive 6 from the negative side. Not approaching negative 6. Approaching 6 from the negative side, which means what? To the left or to the right of 6? From the left. So you want values, you want a sequence of values that are sneaking up on that 6 from the left. So use those or use the graph to come up with this limit. this one numerically is a little bit tough because it's tough to get convincingly close enough to 6 to really see what's going on. You can. So x should be so make that
So this is the right.
that'll work. You might need to change it if you see the you probably gonna use let's hit zoom 0. Let's see. Let's see what that is. Okay. So there is x equals 6. You should do this refresh. Okay, so like I said, there's a couple ways you could work on it. Working on it numerically is challenging, so I'm going to look at it graphically first. I've already got the function plugged into my calculator, so I'm going to set my window between -5 and 7. I don't want to go all the way up to 6, or I don't want to cut it off at 6 because I want to see a little bit beyond that. Zoom 0 should give me a nice fit to the graph. And so as you're coming in from the left, that is from the negative side of 6, where's the function going? What's the limit? Yeah, -infinity, right? Now, it's tough to see that numerically. If you're chasing after this numerically with a table, and there's nothing wrong with that, 5.9, 5.99, 5.999, it's kind of getting towards -infinity in its own sweet time, getting there really slow. So it's not as convincing as maybe we might like. They are keeping, the trend that you do see there is they're continuing to get bigger and bigger in the negative direction. But it's not like overwhelmingly fast. And eventually your calculator is just going to round it up to a 6 because you're going to put in so many 9s, and you'll get an error. So there's a little bit of a limit as to what you can do with it on a table. Yes, sir?
Is there a way to like switch surroundings on the tables so that you can get more exact values?
Not that I know of. It's a great question. I don't know of something you can do there. One thing that I will point out, I don't know, maybe I pointed this out to you guys before, or maybe I pointed out to my morning class, but here, I mean, you only see a few digits, but if you wanted more digits for the y value, put the cursor to the right, and at the bottom you'll see more digits. So at least on the y coordinates you can see more. All right. Bottom line here, the answer should be -infinity as x approaches 6 from the negative side. Looked at the graph. Graphically speaking, as you approach 6 from the left, that's heading down towards -infinity. Yeah.
My calculator would not draw the whole graph all the way down.
Might have to do with your window setting. So what's happening with your calculator is that your calculator takes your window, you know, whatever your x min and x max is, and it divides it up into, I forget, like 250 some points, and it just plots points. So what's happening with yours is that the next point down is off the screen and it's not playing connect the dots. So if you had a different window setting, say instead of going with what's called the standard window setting, negative 10 to 10 in both directions, let's just do negative 7 to 7. And then I'll let the calculator do the rest. So I'm going to hit zoom 0. And let's see what happens there. And that's looking a little bit better. Okay, so play around with it a little bit. Yeah, I mean it's an acquired skill, being able to graph these things. I will, as best I can, try and show you as many tricks as I can without overwhelming you. Let's look at problem number 30. And before we graph this, before we look at the graph, I want us to look at the function and maybe make a prediction. F of x is x squared minus 1 over x plus 1. Now, where is this function going to have issues? Where are we going to have problems with it? At negative 1. So at negative 1, all right, there's going to be issues. But what kind of issues? Well, let's see here. I'll notice for you that the numerator will factor. And if the numerator factors, well, there's still going to be a problem at negative 1. You still can't put in negative 1 into this function. But is it going to be a catastrophic failure? Am I going to have a vertical asymptote, or is it going to be something else? It's going to be a hole. There's going to be a hole in the graph because you've got a term that's going to cancel from the numerator to denominator. Basically, this function is going to look like x minus 1, except it's going to have a hole at negative 1. Now we can see that. In fact, you know what? Let's set that up on our calculators. So to see that on your calculator, let's plug in the function with parentheses x squared minus 1 divided by x plus 1, like that. In order to really see this, I would suggest that we put negative 1 at the center of the action on our axis. So let's go, say, from negative 2 to 0. That puts negative 1 in the center of things. Now hit zoom 0. What do you see when you graph this? What's interesting about this graph? Or different? Yeah, you got a hole, right? And that hole is a discontinuity. What kind of discontinuity is that? A removable discontinuity. Yeah. So that one's a removable discontinuity. Movable discontinuity. At x equal 1. Or excuse me, x equal negative 1. Okay. And that's it. That's all they're looking for in that one. Let's try problem number 38. F of x is 4 over x minus 6. And I want to look at this function and decide, what to expect regarding its discontinuities. Where is this one going to have issues? 6. So at x equals 6, what kind of discontinuity is that going to be? Removable or non-removable? Non. A removable discontinuity is going to have something that's going to cancel out with it, effectively making it irrelevant. So this one's going to be a non-removable discontinuity. So at x equals 6, there is a non-removable discontinuity. In fact, there's a little bit more that we can say about this. In fact, I think you said it, that at x equals 6, you've got a vertical asymptote. That's typically going to happen if you don't have something like this where a couple terms are going to cancel from the denominator. So a quick look at the graph here. Be down here. And you can see that behavior. At x equals 6, you know, the function goes up towards positive infinity or down towards negative infinity. You've got a vertical asymptote at that point in the graph. What can we say about the continuity of this function? Problem number 40. F of x is x squared minus 4x plus 4. Is that going to have any points of discontinuity? Is there a place where you could have a denominator equal to 0? No. You're right if you're looking at that and going, gee, that's x minus 2 squared, but that's only really telling you the shape of this. This is a parabola with a vertex at x equal 2, and it's facing up. But it's defined everywhere. Polynomials are going to be your favorite functions to work with because they're going to be easy to differentiate, easy to integrate. So polynomials are nice. Not only that, but this is continuous everywhere. So f of x is continuous on negative infinity to infinity. Or if you want to be really fancy, if you use this the right way in the right spot, it might give you an extra credit point. It's a script R. It means all real numbers. Yes?
Are you ever going to ask us to find the horizontal and vertical asymptotes?
Theoretically, you should be able to do that because you've taken college algebra, but well, you know, the horizontal asymptotes will come into play soon enough because that's really what you're going to get when you take a look at the limit as x approaches infinity. So the horizontal asymptotes, if I had, say, y equals 3x squared minus 1 over 2x squared plus 7, the horizontal asymptote of this is really going to be the limit as x approaches infinity of that function. You might remember from your work in college algebra that when these two degrees are equal, it's just the ratio of those leading coefficients. So, yeah, we are going to work with that stuff. All right, for now, not yet.
Understand the rule of thumb for this discontinuity stuff? Like how everyone is able to predict.
Sure. So if you have something that's going to cancel with your denominator, then that's going to be a removable discontinuity. If something doesn't cancel with the denominator, then that point is going to be a vertical asymptote, and it's going to be a non-removable discontinuity. So if you get this cancellation, it's removable. If you don't get the cancellation, it's non-removable. Back up here with problem number 10. We got some cancellation. So if you were to graph problem number 10, at x equal 4, there would be a hole in the graph because you'd have a removable discontinuity. But at x equal negative 4, you'd have a vertical asymptote and you'd have a non-removable discontinuity. Okay, problem 64. F of x is 4 sine of x over x, and that's as long as x is less than 0. A minus 2x for x greater than or equal to 0. So this is a piecewise function, and the goal is to try and make it a nice continuous function. Now the question is, why isn't it continuous? The right-hand part of this, to the right of 0, that's just a straight line. Left-hand part, as long as you're not plugging in x equals 0, you should be fine. So where's the problem? Well, let's take a look at the graphs. Here's the graph of the first part. 4 sine of x over x for x less than 0. Here's a graph of the second part. And if you're wondering how do I cut it off, that's what these curly braces are for. X less than 0. So if I got rid of that, I'd have everything. Putting it back and just cut it off wherever I want. So that's the left-hand part of the graph. Yes, sir?
This might be like a silly question, but why wouldn't you just get 4 because of the special limits?
Well, you do get 4
Oh, you do?
on the left, right?
Oh, right, yeah.
But that's the limit from the left. On the right, you know, what you get depends on the value of a. With a equal 1, the height here is 1. But the problem is right here. This isn't continuous at 0, is it? You've got this jump discontinuity. It's a non-removable discontinuity. What we'd like to do is we'd like to choose the value of a that makes this a continuous function. So what value of a? If I slide a around, different values, there is a value somewhere in between that makes it continuous. So we have to figure that out. Now, in order to be continuous, basically what I want is the limit to exist here. So let's calculate the limits. In calculating the limit, if I want that limit to exist here, what two things have to be true and equal at x equals 0? Yeah, the limit from the left and the limit from the right have to be equal at 0 in order for this to exist. So let's calculate both of those limits. The limit as x approaches 0 from the negative side of f of x. Well, if I'm approaching from the negative side, I can replace this with this. That's the limit as x approaches 0 from the negative side of 4 sine of x over x. Can I get a quick answer on that? What's that limit going to equal? 4. That's really just 4 times your special limit from earlier, right? So 4 times 1, or 4. That's the limit from the left. Now I need to calculate the limit from the right. And then I need to make sure that they're equal. So the limit as x approaches 0 from the right, well, instead of writing f of x or 4 sine of x over x, what should I write here? Yeah, a minus 2x. And what's that limit? Well, we want it to be 4, but what is it here? We do a little bit better than that. Just a, right? Because if you plug in the limit, it's a minus 2 times 0, or just a. Now, if the limit from the left is going to equal the limit from the right, what does that say a has to equal? A has to equal 4. In order that the limit from the left and the limit from the right are equal, a has to equal 4. If you go back to Desmos and I change the slider to a equal 4, you see it lines up real nice. Both of these have a limit at 4 when x is 0. All right, so the bottom line, the answer here is let a equal 4. Let's take a look at problem number 94, and then we'll call it a day. F of x is x to the 4th minus x squared plus 3x minus 1. Plug that into your calculators. We're going to discuss something called the Intermediate Value Theorem. Intermediate Value Theorem. And if you just want to watch it up here for a little bit, that's okay too. I'm going to plug in x to the fourth minus x squared plus 3x minus 1. And they're asking you to examine this function on the interval 0 to 1. But let's go to the table function first. I'm going to delete all these old values here. Let's just trash those and plug in 0 to 1 for the x's. What happens with the y values? Where does this function increase from and to? It goes from -1 to 2. Now along the way, it passes an interesting and critical value. Along the way from -1 to 2, it passes through 0. And that's going to be where the function equals 0, where f of x is 0. And where that happens, we have a lot of names for that. X-intercept, roots. Now, the intermediate value theorem guarantees that I can find an x where this happens. A value of x that makes this equal to 0. And that's all the intermediate value theorem says, is that because we're going from -1 to 2 along our y values, it's somewhere in between. There's a value of x that I can plug in that gives me a 0. You can play around with it. It's about 0.37. It makes me pretty close. Let's look at it graphically. To look at it graphically, set your window from 0 to 1, and then zoom 0. And you'll see that, somewhere in between 0 and 1, the graph crosses the x-axis. We've got an x-intercept. Now the book asks you to find that and estimate it. There's a lot of ways you can estimate it. The one that's kind of interesting and helpful, not for problems like this, but in general, is zoom box. You press the zoom key and box. Press enter at a couple points, and then you can change your window. You can zoom in. And then you can keep on zooming in and get as close to that point as you want. In all honesty, though, if you actually needed a point like that, hit the second menu, then the trace key, and find the 0. And then you can find it a little bit faster. Second trace. Yeah, left bound, etc. Now, I'm not going to make you responsible for all that stuff. I'm just letting you know it's available so that you can use it later on. Is there a hand up there? No. For homework, try 1 through 13, 19, 25 through 55, 63, and then a big jump up, 93 through 101. That's on page 99. This is section 2.4.